Okay. Well, we certainly are in a different situation. Uh, so, in case you hadn't heard or see this before, we try to do the Zoom meeting. The AP exam is going to be slightly different. It won't include things like atomic nuclear physics, waves, but it will include thermodynamics, which we haven't done yet. And so basically, what I'm going to do is stop the atomic and nuclear. We were almost done with it anyway, and then just move to thermodynamics. So I'm going to go ahead and get started with that, and I'll give you 3 problems at the end. All right, so thermodynamics, just as the word sounds like, is dealing with heat and the transfer of heat. You've got 2 thought questions on the Google Classroom. Go ahead and go in there and answer those if you have not yet. But as we look at the 3 states of matter, we've got solids, we've got liquids, and we have gases. What we find with each of these is the attractive forces between the atoms or molecules are all electrical in nature. However, when the atoms or molecules get too close, the electrons in the outer shell become repulsive. In other words, the electrons from one atom are repelling electrons from the other atom. And so it doesn't let the atoms actually merge. They keep separate, 2 separate, distinct atoms. In solids, these forces are strong enough to hold out atoms or molecules relatively in fixed positions. And so we can think of it as 2 or more atoms, and we can do this in 2 or 3 dimensions, connected with springs. Okay, so solids, these atoms are held firmly together. They can vibrate back and forth, but they're still pretty much held right to that one spot. They vibrate back and forth, but they don't leave. Now, as we start adding thermal energy to a solid, these atoms start vibrating more and more. They end up with more kinetic energy. So instead of just vibrating a little bit like this, they end up vibrating very big, very big. And as we keep adding thermal energy to it, these atoms gain more and more kinetic energy to the point where all of a sudden they've got so much kinetic energy they break free. Okay? So basically you have a solid turning into a liquid. So these atoms are moving around. They're still attracted to each other, but they're moving fast enough that they don't become fixed in a position. They're pretty close together. They bump into each other. They go around each other. But again, enough kinetic energy that they're all moving around and not attached. So we have here a solid, we have here a liquid. And if we keep adding thermal energy to this, the kinetic energy gets to be so much that each atom goes in its own direction, away from each other, and at that point it's turned into a gas. Okay. So what I want to do is I'm going to start with an example of something in a solid state. And what we're going to look at is the distance between atoms. Okay. The density of copper is 8,900 kilograms per meter cubed. And each copper atom has a mass of 63 atomic mass units. Now we just talked about that. The atomic mass unit is based on carbon, and it is defined as 12 for carbon. And what we want to do is estimate the average distance between neighboring atoms. Okay, so first thing we're going to need to do here is we've got the mass of copper. It's 63 times the atomic mass units, which is 63 times 1.66 times 10 to the negative 27th kilograms. And when we multiply that out, what we get is 1.04 times 10 to the negative 25th kilograms. Okay, well, if we're trying to find the average distance between neighboring atoms, we're going to start with looking at a volume. And we're going to need the density. We're going to have to go back to our formula for density. Density equals mass divided by volume. Okay, so our density is 8,900 kilograms per meter cubed. Put that into our formula here, 8,900 kilograms per meter cubed equals mass divided by the volume. Well, our volume here is going to be 1 meter cubed. Multiply that across. So our mass for 1 meter cubed is 8,900 kilograms. Well, what we're going to need to know here is the number of atoms. So the number of atoms in 1 meter cubed is basically the mass divided by the mass per atom. Right? In this thing, we've got a whole bunch of atoms. To find out the number of atoms, divide that by the mass of an individual atom, and that'll give us the number here. Okay, so number of atoms in 1 meter cubed is 8,900 kilograms divided by 1.04 times 10 to the negative 25th kilograms per atom. Okay, so go ahead and calculate that. Okay, what you should have gotten is 8.5 times 10 to the 28th atoms per meter cubed. Okay, but this is a volume. We're not interested in the volume. We're interested in the distance between two consecutive atoms on average. So our volume is made up of the length times the width times the height. Let me put it this way. Okay, length times width times height. We're going to assume that the distance between the atoms is the same each direction. So basically what we're going to do here to find the distance we're going to take the cube root then of the 8.5 times 10 to the 28th atoms. And when you do that, you get, for your distance between your atoms, or excuse me, okay, hold up, this is the number of atoms in one direction. Getting ahead of myself here. So number of atoms in one direction. And what you should get here is 4.4 times 10 to the 9th atoms per meter. So then our distance is going to be equal to 1 over this. And that's 2.3 times 10 to the minus 10th meters. This, in fact, is not that much bigger than the size of a copper atom. Okay? It is a little bit bigger. It gives it room for those atoms to vibrate as if they're on springs, but not that much bigger. So what we want to talk about now is temperature. Temperature is a measure of how hot or cold an object is. Many properties of matter change with temperature. For example, materials expand when heated, generally. So we have several temperature scales that we use. The one that you're probably most familiar with is degrees Fahrenheit. Degrees Fahrenheit is based on the freezing temperature of a brine mixture. Okay, brine is basically ice, water, and salt. You have degrees Fahrenheit, which is based on the freezing temperature of water. You have Kelvin, which is based on absolute zero. It has the same size units as degrees Celsius, but instead of having zero at the freezing temperature of water, it's absolute zero. There are actually a few more that not too many people use. You have Rankine. It's basically units the size of the degrees Fahrenheit, except it's also based on absolute zero. There's actually degrees Newton. I don't know of anybody that uses that anymore. Primarily, what you'll see is these three, and in science, we almost exclusively use degrees Celsius and Kelvin. By the way, it's just Kelvin, not degrees Kelvin. I don't know why, but it used to be called degrees Kelvin, but then back in the 60s, some international group of chemists came together and decided that they didn't want to call it degrees anymore, and so it's just Kelvin. All right, the final thing that I'm going to do today is talk about what's called the zeroth law of thermodynamics. Okay, why zeroth? Well, they came up with the first, second, and third law of thermodynamics and then decided, oh, wait a minute, we left one out, and it was kind of the starting point should be the starting point for all the others. So we're going to call it the zeroth law. Basically, what the zeroth law does is define when things are in thermal equilibrium. Okay, now it's going to be very formal language here. It says if two systems are in thermal equilibrium, with a third system then they are in thermal equilibrium with each other. Okay. Don't want to get too wrapped up with this. Basically, it says if we have a system here, system A, it's in contact with system B, so we have no heat transfer. Okay, so if this is true, and if system B is in contact with system C, there's also no heat transfer there because they are at the same temperature. If that is the case, then system A is also in thermal equilibrium with system C. Okay, well, that should be kind of an obvious statement. You know, if you've got let's say two objects with the same number of things in it, let's say two bags, each of them having the same number in it, this one equals that one, and you take it over here and B also has the same number in it as C, well then the number in A and C should be the same as well. So this one is just very basic. It sounds like we tried to make something really hard. All it basically says is, hey, if this is the case, these things are equal. Okay, so with that, what I'm going to do is I've got two problems for you. I'll put it in Google Classroom. Basically, it's number 1 from the problems in chapter 13, and then also I believe it was number 2. Double check that real quick. Nope, number 1 and number 3 from the book. But you can just pull the Google Classroom, the problems from there, and work them on that sheet of paper. When you get done with those, go ahead and take a picture and post those. And I'm going to stop there for today. Next time, what we're going to talk about are the ideal gas laws.